Hello everyone! Today our focus is going to be a photodiode, its operation and fabrication. And in order to explain all of that, I think I'm gonna use a simple TCAD simulator I wrote myself. So here it is. And I will just go with you through all the simulator settings and we'll simulate something, and I will be explaining the results and how to optimize the device. Okay, so the whole interface is divided into 3 panels. So simulation is obviously the settings of the process of the fabrication, and then electro-optical simulation of the device. Results panel will display here all the fields, doping, electric field, and so on inside the device, or optical parameters. And then lastly, this is the last panel, is the command line style text output from the simulator. Okay, so let's start simulating. How to fabricate a PN junction? Well, we need some substrate first. So here it is, our wafer. We can go intrinsic, we can do some doping. Let's keep those settings as they are, some initial concentration. Okay. We can also define some epitaxy layer, also some doping, obviously thickness, let's keep it, and then implantation. So here are the actual implants, we can define up to 12 of them. So what we can do here, well, we choose the dopant, we set the dose, the energy, and then 2 parameters related to annealing, so temperature and the time. Okay, electrical tab, few settings here. A PPD pinning voltage. In case we are simulating a PPD, we are not going to do that today. Just a simple single PN junction. But it would calculate for us the pinning voltage of a PPD and the capacitance per square micrometer, and then the temperature for the electrical simulation. And then lastly we have optical tab. So it's the definition of the incident optical power that we input to our device. So very simple range. And then definition of our spectrum. Couple of options here. We can go uniform, so that means obviously uniform power distribution among all wavelengths, but we can do something like a direct sun or tungsten. So you see here, that box, it gives us a temperature. It's like a white balance style color temperature for different sources. So tungsten thermal source, obviously lower temperature than something like a direct sun or just a clear sky. But what we are going to do is we are going to import some spectrum. You can also do that. So that's just air mass 1.5 spectrum. So here it goes from 400 to 1120 nano. And then we set the power. So what this box means is the integrated power, integrated over the whole spectrum that we shine on a device. And then last thing, integration time. Let's keep 1 second as it is. Okay, 2 last things before we start the simulation. We need to set some depth. So actually I will go with just 1 micron first. What it means is how deep in the wafer the simulator will go when calculating the results. So it basically means we are going from the top of the wafer to 1 micron depth. And then lastly, accuracy. We can keep high, 1 nanometer grid. It's a fairly quick 1 dimension only simulation, so that's fine. Okay, I think we can keep those settings and just see what happens. Well, maybe before I even run the simulation, just let's ask ourselves, how do you actually fabricate a p-n junction? Well, p-n junction, meaning you need to create two regions in a silicon, right? P-type and N-type. So we need two opposite type of dopants. And that's exactly what we are doing here, right? Our substrate is P-type already, right? Boron with some initial concentration. And then, okay, we have one boron implant as well, but then that's the key. That's the N-type implant, phosphorus. So that's going to give us the N-type region. Okay, let's run process simulation. You can do that from here, or as well you can hit run here. And that's the cross section of our wafer, that image here. So the top of a wafer is here, and that 1 micron depth is at the bottom of the image box. You can as well go here in the list and plot the actual calculated numbers, concentrations of ions. So the p-n junction happens where that trace crosses 0 on the y-axis. So it's at some 200, maybe 230 nanometers. That's where we have the junction. And in this image here, you can see that it happens, well, you can read from here on the right, the depth where you move the cursor. So now, yeah, about 230 nano, that's the depth where we have the junction. By the way, you can display those results in a more traditional TCAD color palette. I call it universal palette. So that's how it looks like. So obviously now you have your N-type zone here, and then we go to green around the junction where we are again like close to neutral, and then our P-type region. Okay, but let's go to let's turn this off. Let's go to this color palette. That will be actually a bit useful later to keep it on. So let's just run electrical simulation. Okay, it's already done, very quick. We've got some electrical potential calculated, again, versus the depth in the silicon. Let's just quickly take a look into the depletion, how it looks. Okay, so that green tiny sliver is the depletion, right? If I plot this, you see on the plot, the region where it says 1, it means that the silicon, the material is depleted, right? So again, around our junction, very narrow, very tiny depletion region, very small space charge zone, which will have some impact on the performance of the device, you will see. But let's continue and run the optical simulation. Okay, it's also done. And the final result is actual quantum efficiency calculated based on our previous simulations. So what are we getting? Well, you can say that this is a very poor performing device, right? Just slightly over 3% of a QE. The peak is somewhere in the violet or blue, right? Just after 400 nano. And then it decays to 0 very, very quickly. And in near infrared, it's almost 0, right? So kind of a poor performing diode. How is it so? How to understand that final plot we've got? Well, let's start with the position of the peak. Why the peak is in the blue? Well, as we just saw, the junction and the depletion happens at the very narrow depth, and the depletion is narrow itself, right? So as we know, the blue light, blue photons, they are absorbed first, right? Their depth, their absorption depth in the silicon is the shortest. And then the green ones are next, and then the red or infrared photons, that they require much larger absorption depth to actually create electrons to get absorbed, right? So that explains the position of the peak, right? The peak is in the blue because our p-n junction itself is very, very shallow. It's very close to the surface of the silicon. So it's exactly where the blue light gets absorbed, right? And then why the performance is so poor? Well, the assumption that we are making here in the simulation is that the only electrons that contribute to our signal, that get integrated in a diode, that are catched, so to say, are the electrons that are created within the depletion zone. So now let's maybe take a look at the optical layers here. So here it is, the absorbed power. If I plot this, obviously, as you expect, the exponential decay. Generation rate. So these are the the electron hole pairs per second generated in the silicon in our diode. And then if I go again to our transparency mode, and if I do depletion, so you see that that tiny sliver, I will turn it on again, turn it off, turn it on. It happens here, so only that intersection of that sliver and the generation rate layer, that's what finally contributes to the signal that we are getting. And that last layer, photo-generated carriers, is basically that intersection. So we collect very tiny amount of the total photo-generated charge, right? At least by this assumption that we are doing here. Okay, how to improve things? How to optimize this diode? Well, let me do a few things. First, I'm going to decrease the initial doping concentration in the epi. And then for the implants, I will decrease the dose as well to something like that. And let's run simulation. Okay, that's our net dopant concentration. Well, pretty similar. I mean, well, the junction is obviously in the same place. We didn't change the energy, so the implants are, the max concentration will be at the same depth. So the junction is created in the same place, 230 nano. But the dose has changed. So let's see what happens when we run electrical simulation. That's kind of a different image, right? Let's go to the depletion. So that's completely different, right? Much wider depletion. So now we can hope that we will gather much more signal. We will catch much more of many more of those photo-generated electrons, right? Because our depletion is wider, right? And then here we go. That's the net charge within the depletion zone. That's the electric field. So we integrate the net charge. We get the depletion, the electric field. So the maximum is somewhere at the junction itself. And then we integrate once again, and that's the electric potential. And well, how to understand the basic operation of a photodiode? By having this p-n junction and this depletion zone and the net charge and then electric field and finally the potential, we create some force that gathers our electrons, right? That can capture them for us in a diode, like in a bucket, you might say, right? Okay, so now let's go further and let's run the optical simulation. Okay, so now that's what we've got, and that's kind of a different result as well, right? As we expected, we improved the QE right? Now we have about 70% in the peak. The peak itself is still in the blue. That's because the PN junction itself is a very shallow junction still, where the blue light gets absorbed. But at least we have much more efficiency because our depletion got wider. Okay, so now how to optimize the diode even more? Let's plot the QE data again. Let's say that the application of our pixel and image sensor is to create images in near infrared, so somewhere here, right? We see that still the performance here is very, very poor. How to improve that? Well, let me do some other thing here. So I will keep the epi as it is, but I will go to my implants and I will, actually, let's turn off the boron implant. Substrate is P-type anyway, right? We just need an N-type implant in the most minimalistic case, so let's do just that. And I will decrease the dose a bit more. And here, the energy. I'm going to do half a mega electron volt, which will basically create my implant much deeper into silicon. It will move it to the higher depth. And I'm going to simulate for 20 microns this time. So now let's run all the simulations together. Okay, great. So that's what we wanted to have, right? We wanted to have the peak shifted, and we did that. So it was in the blue previously, right? Now it's somewhere in the red region, and you see that clearly we are getting much more QE in the near infrared. And why is that? So let's look into our results. Depletion. If I turn this on, you see much wider depletion. Now, if I plot it, you see it goes from somewhere around 1.5 micron in the silicon to some 10 microns. So we have like 8, maybe 9 microns of a depletion, much wider. And the junction itself is deeper, which means that now, if I go to, let's plot it maybe against generation rate, and if I do transparency again, depletion. So you see now we are collecting the photo-generated electrons from here. Previously, we have been working with the electrons that were generated in a very narrow, or at least relatively narrow sliver close to the surface. Okay, that's all for now. I hope that was a bit useful, and see you very soon.